we go. Okay. So on to how we quantify matter. This is like super straightforward review, you guys. I want you to remember all of the different ways we can convert into and out of the mole. So we quantify matter by measuring in moles. And you can convert between moles and particles using what?
Avogadro's number.
Beautiful. So 1 mole is equal to 6.02 times 10 to the 23rd particles. We can also convert between moles and mass using the average atomic mass that we just discussed. So 1 mole of any substance has a certain molar mass. 1 mole equals some number of grams. And we can also convert between moles and volume. Now, there's a bunch of different ways to convert between moles and volume. It's going to depend what state of matter you're talking about. The 2 most common mole to volume conversions that you're going to need would, 1, be if you had a gas at STP. 1 mole is equal to 22.4 liters. And this is only for gases at STP. We could also convert between moles and volume of a gas using Pivnert if we were not at STP. But the other mole volume conversion factor that you guys need is for solutions, okay? So over here on the other side of my mole volume conversion, I'm gonna put molarity, because molarity is moles of solute per liters of solution. So this would be your mole volume conversion factor if you're talking about aqueous species versus gases. So we obviously use these mole conversion factors not only in dimensional analysis and stoichiometry of reactions, but we can look at the moles of a substance or moles of elements in a substance and determine the identity of the substance. In other words, we can figure out empirical and molecular formulas using molar mass conversions. So let's do a practice problem. That'll wake everybody up.
Oh no.
Yeah, get your calculators out. All right, so let's say I have an unknown substance, right? I come back from my Peru trip with this unknown substance from the jungle, and I run it through a mass spectrometer, and I find that it is composed of 56.5% carbon and 7.11% hydrogen and 36.4% phosphorus. And the true molar mass of the compound is equal to 170.14 grams per mole. I want to know what is the empirical formula and what is the molecular formula of that compound. Can I scroll to the average atomic mass? Forgot to copy it down. Sure. Can you see that, Theo? Okay, you guys. So if you're like, I have no idea what this problem's asking me to do, remember, you want to convert your percentages to mass by assuming a 100-gram sample. So that's easy. And then you're going to go, oops, sorry. And then you're going to go from mass to moles. And then you're going to go from moles to a mole ratio by dividing by the smallest value. And that should be your empirical formula. And in case you've forgotten your molecular to empirical formula equation, the molecular formula is some whole number times the empirical formula. And that whole number you get by dividing the mass of the molecular formula by the molar mass of the empirical formula. All right, so I'm going to quietly work through that problem as you guys do as well. And you can look up and check your answer when you're ready. Okay, so you guys should have gotten an empirical formula of C4H6P. That's my empirical formula, simplest whole number ratio of the elements in the compound. To get the whole number multiple that the molecular formula is going to be, I need to divide the mass, the true molar mass of the compound, which is the 170 grams per mole I gave you, over the empirical formula's mass, whatever that guy's mass is. And that guy's mass is around 85 grams per mole. So we get a multiple of 2. This is my molecular formula. Any questions on that stuff?
Nope.
Cool. Oh, good. Danny's audio is sharp this morning too. Okay, so moving on, you guys. And I'm just gonna kind of like fly through this stuff, right? Because I only have you for like, with all that issues I was having with my screen, we've only got like 25 minutes left. Okay. Electrons. We take this structure of the atom that we talked about, the protons, neutrons, and the electrons, and we move on to 2 different models of the atom looking at where are these electrons. First model is the Bohr model. And the Bohr model says that electrons are in set circular orbits. Remember, like moving in these like 2-dimensional rings, like planets around the sun, okay? However, Theo, that's not nice. Oh my God, that was a good joke. Okay, now, we know that this model is not the most modern model anymore, okay? We recognize that the quantum mechanics is a better model for us to use. But the Bohr model was good for us in the sense that it was the first time that we recognized that electrons have quantized amounts of energy and can move between those energy levels. And so there's 2 equations that you guys need to be able to work with. and I don't think anyone needs to do any practice problems with these. We can calculate how much energy is being emitted by an electron transition by multiplying, this is Planck's constant, times the frequency of the photon of light that gets emitted when an electron falls from a higher to a lower energy level. We could also then calculate the wavelength of light that we see using C equals lambda nu. And this, of course, being a constant, your speed of light. Okay, so this is speed of light. This is Planck's. And these two equations just relate wavelength of light to frequency of light to the amount of energy that gets transmitted. If you guys are frozen and you need to like pop in or pop back out, I'll let you back in. Okay. All right, now, in terms of like what kind of question might you see with relation to the Bohr model on the AP exam, remember this relates to the flame test lab. So like if you'll see different elements emit different colors of light. So we did that back in the unit when we were studying electrons. You'll see what we call specific atomic emission spectra. You'll see different bands of light for different elements, like a fingerprint. And that's because every element has unique energy levels and a unique number of electrons in those energy levels transitioning between those quantized places and emitting very specific frequencies of light. Okay? All right, but the Bohr model obviously cannot explain bonding. The math really only worked out when we were talking about hydrogen. And so if it got, if you had more than one electron, it became not the best model. And so now instead of using these set circular orbits, Heisenberg's uncertainty principle tells us that we can't base electron location on certainty at all because they're too small and they're too fast. So we can't locate them, both their velocity and their position at the same time. So instead we use what we call the quantum mechanical model of the atom. And that quantum mechanical model of the atom is based on probability, not certainty. And we call these things, these S, P, D, and F things, instead of calling them orbits, we call them atomic orbitals. Okay? And we don't need to go into a big, long conversation about how this model works. I think you guys know. Maybe what we should do instead is let's write an electron configuration for iron. And then we will discuss what this electron configuration can tell us. So everybody, here we go. Iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, I believe. Yeah. Okay. So this is called your longhand electron configuration. And you also want to be able to draw an orbital diagram. So 1s showing the spin of our electrons, remember? 2s, 3 spaces for my px, py, and pz. Remember, we spread the electrons out before pairing them up. 3p. 4s. And I draw all 5 spaces for my 3d, even if they're not all full, which in this case they are. Spread them out before pairing. There's my 6th electron. And we can also do a shorthand notation where we put the noble gas that comes before iron into brackets. And that noble gas is going to be, I think it's argon. and then we write the configuration that comes after. We use electron configurations to help us identify valence electrons. So my valence electrons are my electrons farthest from the nucleus. There are my valence electrons. The 3d6 is slightly higher in energy, but it is not as far from the nucleus as the 4s. Okay, so yes, these transition metals have d block electrons that are a little bit higher in energy, but they're closer to the nucleus than the 4th energy level. So iron has 2 valence electrons. If I was looking at an iron ion, I would most likely predict that iron would make a 2+ charge because it would lose those 2 valence electrons. But don't forget that iron can also lose d block electrons. So when the transition metals lose electrons, they first lose from their valence shell, and then they can lose from their d block. So if all that iron lost were those 2 valence electrons, it now has the same electron configuration. Well, no, it does not. Sorry, I'll talk about something else. If it would just end with 3d6. However, iron can also lose from the d block. And if it were to lose an additional electron from the d block, if one of these, if this electron were also to come out, iron could make a 3+ charge. And of course, we indicate that with our Roman numerals. So that's the iron 2 ion, that's the iron 3 ion. So take from the valence shell first when you're looking at electron configurations and how these atoms lose electrons. Okay, any questions on those electron configurations and the rules for writing them? All right. So another graph and type of thing that you're definitely going to see on the AP exam. Sorry, I know this is kind of light. Ooh, sorry, a little washed out. On the y-axis right here, you've got your relative numbers of electrons. So like the peaks here are representing how many electrons are in that orbital. And binding energy is the same thing as ionization energy. It's how much energy you need to put in to remove those electrons from those orbitals. And what's confusing about these graphs is they go from high to low. So be careful when you read the x-axis. So if I'm trying to figure out what atom does this represent, I just need to look at the relative numbers of electrons and how much energy those orbitals have. So obviously the orbital that is closest to the nucleus is going to require the highest amount of ionization energy in order to remove those electrons. So closest to the nucleus is my 1s. And then the next is my 2s. And notice there's like 2 electrons in my 1s and 2 electrons in my 2s because they're the same height. The next orbital is the 2p. And relatively speaking, that looks like 3 times the height of this other guy. And then my next orbital, and like, whoa, like way out here, much larger orbital, my 3s, and then my 3p. But if I was reading this graph, do you see how this peak is not nearly as tall as the 2p peak? That means that this guy is 2p6, right? So this has 2 electrons in it. This one has 2 electrons in it. The 2p has 6 electrons in it. And the 3s has 2 electrons in it. And I would have to estimate, like, is this half the height? Sure, looks like it's half the height to me. So I would call that 3p3. And so if it's 3p3, I just go to my periodic table to my p block, 3rd period. And what element is that? Phosphorus. So that would be, this would be phosphorus. These things are called PES, stands for Photoelectron Spectroscopy. And it's just a way to identify unknown elements. We can also identify mixtures as well and compounds using this type of technology, where basically we shoot in radiation and measure the speed at which it ejects those electrons. And the speed that the electron is traveling will relate to how much energy was required to pluck that electron off. In fact, we could write that as an equation, but I don't think you guys need it. I just think you guys need to be able to identify an element and read that graph. Okay. And then lastly, our last bit of review would be periodic trends. Okay, and the three things that you should be able to recognize on the periodic table as far as trends go, the first being radius. So when we go down a group, radius gets bigger. Aren't those good circles? So when we go down a group, radius increases.
The middle one's almost a perfect circle.
Thank you, Danny. But then this one's like a lopsided pumpkin off to the left. Okay. Now, you do need to understand why radius increases when you go down a group. And if you just think about the electron, everything, you guys, can be explained with electron configurations. So like when in doubt, write out your electron configurations. So when we go down this group, we're going 1s1, and then lithium ends with 2s1, and sodium ends with 3s1, and potassium ends with 4s1. These s orbitals keep getting bigger and bigger and bigger as they layer all of those atomic orbitals on top of one another. So when you go down a group, radius increases with that increase in principal energy level. When we go across the periodic table, radius decreases. So when we go this way, radius decreases. And the reason why radius decreases when we go across is because we are increasing the number of protons without increasing the principal energy level. In other words, when I go from sodium to magnesium to aluminum, I'm going from 11 protons to 12 protons to 13 protons. But I'm still in the third energy level. Like when I go across here, it's the 3s and the 3p. I'm not increasing energy levels. And so when you increase the number of protons, but you don't have an increase in energy levels or layering of orbitals, that increase in the number of protons pulls those electrons in tighter. Do you guys remember? Maybe you should go back in your notes. If this does not sound familiar, I want you to go back into your notes and I want you to read about radius. And remember Z effective? Effective, this is called effective nuclear charge. Oh, somebody's probably chatting something nasty to me about effective nuclear charge. I can't see the chat, hang on. If it's a nice question, I'm gonna feel bad that I said that somebody was saying something nasty. Oh, yes, good, Theo, Z effective, that's right. Okay, Z effective is a measure. All you do to calculate Z effective is you take your number of protons minus your number of core electrons or non-valence electrons. And when you go across a period from left to right, your Z effective increases. You're going to see that when you go back and you practice with this and you calculate it. With that increase in the effective nuclear charge, you get that pull of those outermost electrons in tighter. When you go down a group, because of the shielding effect of all of those layers of electrons, when you go down a group, Z effective is constant. It stays the same when you go down a group. And so those additional protons going down a group do not increase the pull. And so those layers of electrons can get bigger and bigger and bigger. If you understand radius and this Z effective conversation, ionization energy and electronegativity will totally make sense. So when we go down a group, ionization energy decreases. Ionization energy being the amount of energy needed to pluck off those valence electrons. Think about it. If the electrons are really far away, they're easier to remove. Versus when we go across the periodic table and the radius is smaller, your ionization energy increases. Helium is really, really small. the electrons are super close to the nucleus. So plucking off that electron is really hard to do. Oh, you guys, hello. Let's make sure we know this equation, your favorite. Like this is what is governing our electrostatic potential energy. This is the reason why when you have a small radius or a small distance between your charges, big electrostatic potential energy. Okay, so that's what's governing that trend in ionization energy. It's all about the radius or the distance between those charges. Okay, and then lastly is electronegativity, which is love for electrons, being able to attract electrons in a bond. Well, think about it. Big radius between the atoms, not going to be able to very effectively pull on another atom's electrons. So electronegativity also decreases when we go down a group. And across a period, electronegativity increases. So it's the same trend, nice, audible yawns this morning. It's the same trend going across the period as it is for ionization energy. So ionization energy and electronegativity have the same trend, but they are different things. Electronegativity being love for electrons in a bond, and ionization energy being the energy needed to pull those electrons off of the atom. And they can all be explained with radius, and radius can be explained by Z effective. You did it. We did it. Yay, you survived your first 9 a.m. class. I'm gonna stop recording.